Okay, this is part 2 of ionization energy. In the first part, we talked about how Z effective helps determine the periodic trend of ionization energy. And we noticed that as we go across the periodic table, ionization energy increases due to the fact that the Z effective increases, and ionization energy decreases as we go from top to bottom on the periodic table, because we're adding more and more shells to the atom, so the valence electrons are further from the nucleus, and so that makes them easier to remove. So what I want to talk about in this video is, we know the trend is increases as we go across. We know that it's decreases as we go down. But in the periodic table itself, there are some anomalies that occur in this trend, and we need to know why those anomalies occur. So if we look at the next slide, this is a plot of first ionization energies versus atomic number. And what's interesting about this is that you keep hearing that we call this a periodic table. Well, you can see the cyclical property as we go from left to right across the periodic table. You can especially see it here. Here's lithium, has a very low ionization energy, has a very low Z effective of 1 positive. Here is neon at the end of that period, has 8 electrons in its outer shell, and has a high Z effective of 8 positive, and so that makes it very difficult to remove the electron from the atom. So the trend is, as we go left to right across the periodic table from lithium to neon, ionization energy increases. When we look at period 3, we see the same trend. Sodium, very low ionization energy. Argon, the highest ionization energy in that period. And again, we see the trend as we go from left to right across the periodic table in period 3. We see an increase in ionization energy. And you can compare period 2 to period 1, and you notice that it looks pretty much the same as far as the pattern goes. So that's a cyclical property, and that's why we call it the periodic table. Now, I agree they're not exactly the same, and what you notice is that the ionization energy for sodium is less than the ionization energy for lithium. You can see it more dramatically between neon and argon. But that follows our trend too, that as we go from top to bottom on the periodic table from period 1 to period 7, we do see a decrease in ionization energy due to adding of an additional shell to the atom and less influence of the nucleus on that outer shell electron or electrons. So this looks a little different than the other ones, but that's the transition metals in there. So that's why this look. But if you would take those out, it would look very similar to what we saw for period 2 and period 3. But we do see some places where the trend is not being followed. We see it here, and we see it here, where the trend is not followed and that the ionization energy actually decreases. So we need to know why that happens. So take a minute and let's think about, maybe you want to hit pause on the video, and I want you to see if you can figure out why you would see a difference or a decrease in ionization energy in group 13 and group 16. Group 13 and group 16. So hit pause and see if you can think about it, figure it out. All right, hopefully you've come up with an idea. If not, let's talk about it. So let's look at what element is in group 13. So in group 13 in the second period, we would have boron. So boron would have 2 electrons in the 2s, and we had just placed the first electron into the 2p. Well, the 2p is higher in energy than the 2s in a multi-electron system, So this is like we would climb up a rung on the ladder, and this has a higher energy, and there is repulsion of this electron with the 2s in that. If you think about it, we have the 1s, the 2s, and now we've put our first electron into a p orbital. Well, that p orbital is going to create quite a bit of electron-electron repulsion. So, being of higher energy, some electron-electron repulsion, it makes it easy to remove that electron. And so that's the first ionization energy, removal of an electron from a single gaseous atom. So that's IE1. So there's a drop there. By removing this electron, we've eliminated a higher energy electron, and we've also reduced repulsion. All right, let's look at the next element. The next element would be oxygen. Oxygen would have, again, the 2s electrons. And then how many electrons would be in the 2p? 1, 2, 3, 4. All right, so oxygen being in group 16 should have 6 valence electrons, and there they are. 1, 2, 3, 4, 5, 6. So this is the first time that we have paired 2 electrons in a p orbital. And so we have not only electron-electron repulsion between the s and the p, we also have electron-electron repulsion between the 2 p electrons in the same orbital. And again, higher in energy than the 2s, so that makes it easy to remove that electron. So again, that would be IE1. That would be the first electron to go for oxygen, but it would be easier to remove. So what we see is there's an anomaly in group 13 and up here at group 16. So group 13 and group, I don't know what, group 13 and group 16. We see the same thing here. This is aluminum, and this is sulfur. All right? So the trend is, yes, it increases as we go across from lithium to neon, from sodium to argon. It decreases as we go from one period to the next period to the next period. But there are anomalies that you have to be aware of in groups 13 and group 16. Now, it's important that you know these anomalies because the next concept we're going to talk about is electron affinity, and it also has anomalies, and you will see the relationship between the anomalies of ionization energies and the anomalies of electron affinities. But another thing to remember about this plot is the cyclical property. You see why we call it the periodic table. And the other thing that's important is that this is showing you why generally the nonmetals tend to be negative ions and the metals tend to be positives. The metals have lower ionization energies than the nonmetals do. And so, much easier to remove an electron. It costs you energy. It always costs you energy to remove an electron, but it's less energy to remove an electron from a metal ion than a non-metal ion. And again, that's back to Z effective. Z effective is higher for nonmetals. All right, so this is a slide just re-emphasizing what we see in group 13. And also remember, I call this group 13, again, the old naming system, this is called 3A. So you'll have to know both of those, okay? Both of those. And then the next slide shows us the anomaly that occurs in group 16, or also called 6A. All right, the last slide I want to talk about, and finishing up ionization energy, is why is ionization energy so important? Well, this is a really important table, and I'm not asking you to memorize it or anything, but this is showing successive ionization energies. Like if we take an element, we remove 1 electron, 2 electrons, 3 electrons. So we're going through not just only IE1, what we've been focusing on, but IE2, 3, and so forth. So you say, why is this so important? So what if I said, tell me which element in period 3 would you see a huge increase? Oops. Yeah. Increase in, let's say, the fourth ionization energy. The fourth ionization energy. Now, you will have to be able to tell me what that element is without looking at this table. And why this is so important is, let's say I have an element isolated, but I don't know what the element is. One of the things I could do is determine its ionization energies. And from its ionization energies and its mass, I should be able to determine what the element is. So, which element in period 3, oops, I didn't put the 3 there, in period 3, would you see a huge increase in the fourth ionization energy? So what you might start off with is you say, I think it's fourth ionization. I think it's maybe silicon. Let's say if you said silicon in period 3. So you would say silicon has 14 protons, 2 electrons in the first shell, 8 in the second, and 4 in the third. All right, this is silicon. So the first ionization energy costs, well, we don't have silicon on here, so that's not going to help you on the table. But it's going to cost you, what? Something like carbon, probably, and a little less than carbon because silicon's further down on the periodic table. So we'll say, just approximate maybe 950, all right? So 950 for the first one, all right? Second one is going to cost you more because now you only have 3 electrons here. But nothing's changed here, nothing's changed in the core. You still have 8 in the core here, or 10 total in the core. So you'd expect it to go up. The third ionization energy you'd expect to go up too, because now you've only got 2 electrons with a Z effective of 4 positive. And then you remove the fourth one, and that would be quite a bit more than the second one or the third one but the fourth. So the fourth one's going to be larger than the second or third one. But the one that really shows a huge increase for silicon would be the fifth ionization energy. And you go, why is it the fifth one? Because when we go to remove an electron from what was the core or the inner shell, what happens to Z effective? For these 4 outer shell electrons, Z effective was 14 minus 10, so a Z effective of 4 positive. When we go to remove this 5th electron, the Z effective is now 14 minus the inner core now, which is 2, because this is now the outer shell, this is the inner shell. So 14 minus 2, it's jumped up to 12 positive. So we don't have silicon here, but you can see the same analogy with carbon, which is in the same group. So the first one's 1,000, second one 2,300, 2,400, next one 4,600. The fourth one is 6,200. The fifth one, though, is 37,000. 37,000. Because you're removing from the inner core of carbon. So, which element in the period 3 would you see a huge increase in ionization for? Well, it's not something that has 4 electrons in the outer shell. It's something that has 3 electrons in the outer shell. So let's look at aluminum right next to it. So 13 protons, 2 electrons in the first shell. Again, this is aluminum. 8 electrons in the second shell and 3 electrons in the third. So yeah, to take the first electron, that would be kind of like a little less than boron, right? Because aluminum's right below boron, so less than 800. Next one, maybe 1,500 or 1,600. Next one, maybe 2,500 or something like that. So that's the first 3 ionization energies, 1, 2, 3. But when you go to remove the fourth one, that comes from the inner shell. And Z effective is now 13 minus 2 for this one. 13 minus 2, the Z effective is 11 positive. Whereas for these 3, it was 13 minus 10, and it was 3 positive. So the answer here is aluminum. Aluminum. Because when you go to remove the fourth one, it comes from what was a core shell or inner shell. So I want you to be able to do this. This is a common quiz and test question. It allows us to figure out if you understand successive ionization energies. So it's important that you understand the definition of ionization energy. You can draw the chemical equation for ionization energy. And then you can discuss the trends and anomalies of ionization energy. And ultimately, you can tell me through successive ionizations and which period you could determine the element. Why is this so important? Why is ionization energy so important? Because I hope you can see, after talking about the trend, that you can see why metals tend to form positive ions and nonmetals do not tend to form positive ions. All right, the next video will be on electron affinity, which is where a neutral atom gains an electron. Thank you.